Hey, what's up? I'm Liz, and today is a very special episode of Blitz City DIY. We have a special guest, but first, a bit of an intro. I've done a couple of pedal teardowns, and I've talked about music things before and guitar things before on the channel, and I have recently gotten back into playing guitar pretty regularly, which is really awesome for me as a musician to be back in the swing of that. For anyone that's ever kind of fallen out of that habit for various reasons, basically lack of time, you know how great it is when I'm back in. And one way that I've been playing around is I've been listening to a lot of Battles and Rat-a-tat and playing a lot of that style of stuff. And if you know anything about those bands, you know they have kind of funky sounds. So I've been kind of doing like more experimental tones, and a lot of that came with using Electro Smash's time manipulator pedal, Electro Harmonix monosynth pedal, both things I've talked about on the channel. And I'd had my eye on a pedal from Alexander Pedals called the Marshmallow that they released fairly recently. But I've been holding back, and I finally went for it in October when they did a special, very super pink run of all their pedals, actually, in honor of breast cancer awareness. 10% of the proceeds went to a breast cancer specific charity. I've unfortunately, I'm sure you probably have too, had people in my life that have fought breast cancer. Some have unfortunately passed away. So I posted some messing around, some noodling I was doing with the Marshmallow, and mentioned I was going to be doing a teardown of it because why not? And Matthew, who is the proprietor of Alexander Pedals, contacted me after seeing that. Apparently had seen my teardown of the MIDI Baby, which is by Disaster Area Designs, which is the same kind of conglomerate, liked it, and asked if I'd be interested in having him on a call to go over the teardown of the Marshmallow, go over the circuit, everything like that. So that's what this video is. It's going to be this kind of long-form podcast-style teardown where Matthew just steps through everything Marshmallow and also the Neo series pedals in general and pedal building and guitar pedals. It's just really, really awesome conversation that we had. And I really want to thank Matthew from Alexander Pedals, so generous with his time, super nice guy, went into so much detail and was so thoughtful in his explanations and so kind to share his knowledge. And again, the time, I really appreciate, was so much more in depth than I was expecting. I really appreciate it. I think this is a really excellent conversation. There's even more that I could release later on for the sake of keeping it more specific to the teardown of the Marshmallow and kind of everything involved from the hardware, the circuit, the code even, because this is rocking a SAMD 21 in here, so there is some coding aspect to this, and also the design. I mean, look at this design, and it does match the tone. So I'm gonna stop waffling on and let Matthew take over. I hope you enjoy this.
One of the things that we've done is we've got this tactile switch here. It's the original ones we used are CTS D6Rs, but it's a tactile mechanical switch.
Okay.
And we use that for mode selection and for other stuff. So a mechanical switch, a momentary button, is a lot more useful than, say, a toggle switch. So the toggle switch, it stays in a state. Once you move it somewhere, it hangs out there, and even if you, say, change a preset or load a different mode or something like that, the toggle switch isn't going to change to reflect that. So if you had, say, 3 sounds on the pedal, up, middle, and down being 3 different sounds, and you move the switch around, when the user loaded a preset, the toggle might not match the sound, and that can be confusing. So what we've done is we've used the single button here with a single pin on the microcontroller to do a bunch of stuff. So we watch the switch, and if we see it pressed and we do a certain thing, change the modes usually, And if we see it held, then we go into the alternate knob mode. So if you play with the pedal, you'll know that a lot of the user interface stuff has to do with pushing the center button and then turning the knobs. And it's designed so you can do it one-handed, which is why it's down here rather than in the middle. Because if it's up here, then you can't reach down. And if you had to push here and reach down, it's inconvenient. So it's designed to be used one-handed, because half the time you've got your guitar in your other hand. So
definitely, yeah. That's really cool.
Your Marshmallow is a lot cooler looking than mine,
I
have to say. So if we flip it over, you see your Marshmallow and my Marshmallow are pretty much the same. My Marshmallow has a bodge wire here.
Oh, okay.
Let me see. And it goes from the bottom of this cap, it's Charlie 22, up to the V pin of the LED. So the main LED is a WS2812.
Oh, okay. So NeoPixel.
So it's I don't know that Adafruit sells the through-hole version of that. Most of the ones they sell are the 50/50 size SMTs, which we tried that on the prototypes. We had the 50/50s in a light pipe, but we were able to find these on AliExpress for a lot less money.
Oh, cool.
And they look more normal. It looks like a normal LED.
Right.
The 50/50s don't have very good color mixing. So a lot of what you have to do with the 50/50 is put some kind of diffuser on top of it.
Mm-hmm.
So if you want to actually have the colors mix, if you look at most of the LED tapes and things like that, the colors are mixed by a piece of silicone that encapsulates the strip, or they're put behind something so you can't see the LED, you just see the LED reflecting off of, say, the wall behind the TV or whatever.
Mm-hmm.
These are diffused, and you can still see the colors, especially at low brightness levels.
Yeah.
If you crank the LED brightness, it's one of the user settings. If you crank it all the way down and you turn it on, some of the colors, yellow, there's a light green, there's a couple that you can see the LEDs. The white is particularly bad because at low brightness levels, the white looks very sort of pink because the human eye sucks at the color blue. The human eye is just not meant to see blue, unfortunately. Okay, so you got yours, I got mine. I have something you don't, and that is I have the printed schematic.
Oh, very cool.
So we can do a teardown, or we can just go through the whole thing and talk about what works and what doesn't. So astute viewers will note the Spin FV1 chip here. This is a really convenient audio DSP part. It's designed to work like an analog part. So if you look at it with pin 1 facing up, so ours is mounted upside down, and I'll explain that. All the analog stuff happens in the first 4 pins. So pins 1 and 2, and then 27 and 28 are the analog ins left and right, and analog outs left and right.
Okay.
And so all the digital stuff, this cap is for there's a bias voltage. So the chip runs at 3.3 volts, and the A to Ds also run at 3.3, and they're internally biased to 1.6, roughly, 1.65. They're biased to half of 3.3. So this cap and this cap handle some of the internal biasing, buffering of the A to D inputs and outputs. So these two tantalum caps, they're 22 microfarad tantalum caps. And then we don't use a clock crystal on ours. They have a PLL built in, and normally it goes into this pin here. What is that? 14, 13, 12, 11, pin 10. That's X1 and X2, so these 2 pins. There's a PLL in there that multiplies the clock up to the internal frequency that the chip needs. It runs in the sort of 32 times what you feed it.
Okay.
I want to say that's the multiplier. So if you feed it sort of the 32 kilohertz, which is normal, 32 kilohertz is really commonly used on FV1s because you can get 32.768 kilohertz watch crystals for nothing. And it's also a really convenient thing because it's got 32,768 words of delay memory, which means that if you clock it at 32,768, you get 1 second of delay out of it. So the maths become really, really easy.
Oh, that's awesome.
What we do is a little different. Instead of using the internal clock crystal, we just feed it a 3.3 volt square wave at the clock frequency that we want.
Okay.
So we actually generate that on, and yours is more visible than mine. We mark these in production. Mm-hmm. We're not trying to hide it. We just mark them so we know we've put the bootloader on them. So when we bring these to life in production, generally we'll break them out of the pack. They're built on a big frame, so there's a panel of 6 that gets built, and we get them on the panels. So we break them off the panels, and then we use the SWD header up here using an Atmel ice, and is it an ice? Yeah, it's an ice. And then we use OpenOCD to burn a bootloader in there. And for anyone who cares, it is a USB mass storage class bootloader that was developed by Justin Madair at Madair Tech. He developed it and he tweaked it slightly for us to fit some of our parameters. I'm not a bootloader level hacker kind of guy. I'm a slightly bigger picture kind of guy.
Gotcha.
But why reinvent the wheel when he's already made something so good and perfect?
Yeah, so definitely.
We burn the bootloader on it, and then when you put the USB in while holding down this foot switch, which I think is PA9, then this enumerates as a mass storage class device. So you can feed it on a Mac. It's a little tricky because Macs put resource forks and dot files and other things in the file system that you probably don't want. Mm-hmm. On a Windows machine or in Linux, it's a drag and drop. So you literally just drag a file named flash.bin over to it, and it does a block copy of that file into the flash, and then you're done. On a Mac, we used to use the terminal and the copy command, just CP, but as of, I want to say High Sierra, that's broken. Maybe Sierra. It broke fairly recently. So from Sierra on, we use DD, which is the sort of direct disk I/O routine, and DD is in every Linux distro and Unix. It's going back to like Bell Labs in the 70s. So DD's been around forever, and it works great. So we actually have a little wrapper that I made, and it's just some Apple scripts, and it just prompts you for where's your firmware file, where's the destination, and then it runs DD with the correct IF and OF command, so it's pretty easy. So anyway, back to what we were talking about. This is an AT SAMD 21E17, so it's the 32-pin TQFP variant with 128K of flash. I should have used, and this is hindsight here, I should have used the G version with the 48 pins, sort of the same one that's in the like Arduino M0 or Arduino Zero, same thing. Mm-hmm. And the reason for that is the extra I/O gets you access to the circoms. There's 6 circoms in here, but if you look at the pin mux table, on the E, half the pins you need to break them out are not available. They're just not bonded. So they exist, but you can't do anything with them. So they're on the die, but you can't touch them. It's all the pins for the G, E, and J are all on the same die, and just when they bond them in production, they, I don't know, laser etch something, and they set some switches, but they all have the same cores. So on these SAMDs, you pay for the flash, not for the pins. Like the extra pins, it's like 10 cents to get the next pin count up. But if you want to double the flash, then it gets expensive.
It's pricey.
It's my belief they test them in production, and if they don't, probably the RAM, if the RAM doesn't work, then they laser off some switch somewhere and say, oh, well, this only has 16K of RAM or 32K of RAM. So, and then by that same token, the flash is halved as well. So these all go all the way down to, I want to say there's like, the 21 might not be, but like the same V09, there's like 8K variants of that. I'm like, what can you do in 8K on a chip like this?
Yeah.
There's so much overhead for stuff like USB. Like USB is like 16K. Our bootloader is 16K. It's not full 16K. It's like 12 and change. Mm-hmm. It's bigger than the 8K sort of what is the Samba bootloader, the one that the Atmel puts on the chips from the factory. That fits an 8K. Ours is 16K. It's bigger than it's a block larger. So anyway, so we use one of the timer counters on here to feed the spin FV1's clock chip, and we actually use. I can look at this and tell you we use. Let's see. Looks like SWD clock. We actually use the SWD clock line, which is PA30. It has PWM capabilities, and it is one of the only TCCs that has a buffered register, which is really useful. So what the buffering means is that when you change the frequency of the timer counter, basically when you change its count and its overflow, you can have it only change on a transition so that you never get sort of a broken, like it counts halfway up and stops. So if you use the PERB register to do your writes, then it will write and only change when it goes down or up to the other state. And so that prevents glitching on this, so we can change the clock. I mean, it glitches audibly, but it prevents it from crapping the bed, basically. Because if this misses some clock pulses, it needs them not just for the audio clock for the ADDs, but it also needs them to run the PLLs, to run all of its internal stuff. So the rest of the control is pretty simple. We don't feed the chip anything from the pots. So the pots it's all sort of fly-by-wire, if that makes sense.
Okay.
That's how I think of it. When I was a kid, my dad explained to me how the F-14 Tomcat works, and that fly-by-wire has always stuck with me. So the pots go to the micro, and then the micro interprets them and feeds the right values to the FV1. So the FV1 has three what they call pot pins. So it has two ADDs for audio and two D-to-A's. So the ADDs they're successive approximation DACs and ADCs, and they're pretty good. I guess technically delta signal, but they're not bad. They're on the noisy side, but it's workable. And then with the pot inputs, they are 24-bit. So you've got 24-bit by whatever clock frequency. The fastest I've been able to get it to go reliably is about 72 kilohertz, which is better than CD. So it's fine.
Yeah.
The DSP pot input, so 22. So if you look at the FV1, those are pins 21, 22, and 20. So they're on the right side over here if you're looking at the chip. Those are 9-bit ADDs. So they go 0 to 512.
Okay.
Yeah, those three guys right there. They go 0 to 512, and those are used for controlling things in your program. So when you write an FV1 program, and we should probably do like a whole video about here's how you write FV1 code, because it's fascinating. It's a really cool chip. It's really widely used. Like we use them in JSPLIS, Earthquake, or Keeley, and Walrus, and everybody uses them because it's a really convenient way of getting digital audio out of a sort of $200 price point pedal. So those three inputs, these pot inputs, are for controlling stuff. So in your program, you say, read into the accumulator the value contained in pot 0. And the values of the three pots are always available to your program, and they're treated like constants. So you say, RDAX, which is reading to the accumulator, pot 0, and then you give it a scaling factor, so like comma 1.0. That means read it in and scale it by 1. If you put in RDAX pot 1 0.5, it'll read it in and it'll multiply it by 0.5 before passing it to the accumulator. So it leaves the value in the accumulator for you to do something with it next. So writing code for these guys is all assembler. Now there's a graphical application. It's a Java app that was written sort of a guy named Andrew Kilpatrick wrote a thing called ElmGen, and then Digital Larry, a guy, his name's actually Gary, wrote a Java-based sort of build it block-based editor for FV1 code, and it works pretty well, but it's highly inefficient in terms of code space because it just has to be. It doesn't understand how to optimize the code. It says, oh, write this in here, read this in here, and so it does kind of everything twice. So it works, but it's way faster and easier to write in assembler if you know how. So anyway, we read pots. Microcontroller sees voltages on the sort of typical 10-bit A to Ds, 0 to 1024, and then we scale them down to 0 to 255 and feed them over here. And we're literally just using we've got the prescaler set pretty high, so we're outputting 100 some odd kilohertz. Just if you have it lower, you get heterodyning. The idea is if you've got stuff that moves around inside, if you're doing mixed signal stuff, if you've got signals that move around, so if you have a PWM signals or analog stuff, try to keep their frequency bands far enough apart that you can filter out the stuff you don't want. So we've got some filters in our audio stuff that filter out everything above, say, 30 kilohertz, and then our PWM stuff is all at 100 kilohertz. So we don't have to work very hard to get them to be filtered. You will notice, or you may notice, that I'm actually using every single available pin on the microcontroller. If there's a pin, I'm using it. Unfortunately, the only light in this room is behind me, and so I'm casting a shadow on my stuff here.
It's all good.
But I'm using every pin on the microcontroller, every single one.
Wow.
So this is why I should have used the G, because if I'd used the G, I could have gotten rid of some peripheral stuff. So here's an example. In the middle of the board, there is a 74HC595, which is an SPI or a serial input parallel output shift register. So that's this guy here, U2.
Okay.
And U2's job is to get me more digital I/O or more digital outputs. So what I'm doing with U2 is, here's U2, and the DSP chip has 3 address inputs. So it has 3, they're called S1, S2, and S0, and they select the algorithm. So there's 3 bits, which means you get 8 selections. So 2 to the third is 8. And rather than interfacing them directly to the microcontroller and wasting precious pins, which I have none of,
right.
I'm using this, because they don't need a PWM or anything like that. They just need to be on or off. So the shift register doesn't care. It'll give you an on or off. And so the upper nibble of this connects to 4 LEDs, and the lower nibble is the 3 address lines, and then we have one that says DSP mute. And if you look, it's hard to spot, but there's an SOT238 chip down at the very bottom by the left foot switch is the bypass foot switch. So this little tiny, stupid little chip down here, this little guy here, is a DG449.
Yeah,
it's a DG449 analog switch. And that is my great shame and sadness, unfortunately. The DG449 is a high voltage single SPDT analog switch. And high voltage is important because all the guitar signals are sort of around 5 volts peak. The DSP can handle 3.3, and a hot guitar signal can be over 1. It depends on what it is. If you're running this after, say, a dirt pedal, it can be pretty loud. So you need a high voltage analog switch, because what we're doing is we're actually going through it in series, and when we flip it, we change it from, so it's an SPDT switch. So we go into it on the common pin, and then when we're not using it, we flip it and we connect the input to the DSP to the virtual earth. So it's half the. Do you do much analog stuff? I don't want to.
A little bit, yeah.
Okay, so for your viewers who may not know this, if you have an op amp running on a single supply, the op amp will clip the rails. So if we have, go a big Clive on you here.
Okay, I dig it.
This candy is quite delightful. Okay, so if you've got a signal here, so you have an AC input signal of some voltage, 0 to 8.5 volts. And you run in through a capacitor into your op amp. And we'll draw an inverting op amp just for the simplicity of the whole thing here. And then we go here, and this is R1, R2. So if there's any DC component on this, any AC component on this, we'll go through. DC will be blocked. So we can assume that this side is 0 volts, and then we've got R1 over R2, so the gain of this is negative R2 over R1. It's just a standard inverting op amp. What happens here is if the power supply is normally plus V and minus V. So if the power supply is smaller than the signal coming in, then this will clip. So it'll do this. So what we do is if we run on, if this is earth, this is ground rather than say minus 5 volts or something, or minus 9 or minus 12 is pretty common for analog stuff. If this is on 0 volts, then anytime this signal goes down, so normally it's sort of here and here and here. So we're at this kind of level here. So we have, plus 1 and minus 1. So if it's plus 1 and minus 1 volts, and this is connected to ground, every time this thing goes negative, in fact, every time this gets within a diode drop of the rail, which is sort of 0.7 of a volt, which is pretty close to, so it's going to clip. So it'll look like this. It'll look like this garbage right here, if that makes sense.
It does,
so
yeah.
You'll end up with, so what we do instead is we run our signal in, and then we bias this with a resistor to plus V, a resistive divider, and we put a cap here to keep it stable. And usually we call this VB. V sub B or VB. Mm-hmm. And it's equal to half the supply voltage, whatever that is. So if this is 9 volts here, which in the stomp box is pretty common, stomp box is usually 9 minus a diode drop. So 8.3, 8.4, and their half voltage is like 4.3, something like that. And then now we have here our op amp circuit, the same as we had before. And instead of bringing this to ground, we bring this down to this half voltage point, which is here. So we bring this over here. Cool. So we're adding a DC bias to this. And that basically takes our signal, which is normally referenced around ground. So it's sort of above and it's above and below ground equally, like plus 1, minus 1. And then what we do is we add 4.5 volts to it. And now it goes from 5.5 to 3.5. So it still has a 2 volt swing, but we've added DC bias to it. And that lets this op amp reproduce it without clipping the bottom rail. So there's a lot of stuff in here. Now that I've completely destroyed my schematic, read it now.
Oh, no.
So it's right here, the bias divider. So the bias divider is, there's one resistor down here, the lower left resistor, and then the other one is between the two jacks over here. It's the far right but one. So not quite the far right one, the 10K over there. So if you'll notice that there's all the analog stuff lives between this band here, so this sort of area between the jacks, that level, and the bottom of the board. And there's nothing really digital down there at all. So that all lives in its own sort of area, and that's why the spin is upside down, because I want the analog part of it to stick into analog zone, which is here. Analog zone is about the bottom, maybe third of the board. What made the Neo series possible was I found this, and this is a Sanyo. Now it's on semi, but originally it was a Sanyo. It's an LV3327PV, and it is the coolest little chip in the universe. And I own almost all of them that still exist.
Oh, okay.
Yes, they just went obsolete, and so I bought enough to last me a couple of years. So eventually we're not going to be able to make these anymore because these chips will be unobtainium. But I have bought several thousand of them, so we're good. We're good for a little while. But
wow.
it is a volume control chip, electronic volume control chip, that's designed for a personal navigation device, so like a GPS.
Oh, okay.
And it's so cool. So it has 4 inputs, 1, 2, 3, and 4, A, B, C, and D, and it has 2 outputs, and then internally it has 2 voltage-controlled amplifiers, but they're controlled with I2C. So you feed it a number, and you say, okay, I want you to connect input 1 to amplifier 1, or I want you to connect input 2 to amplifier 1, or I want you to connect inputs 4 to both amplifiers. It's a matrix, so you can connect any input to either or both of the amplifiers. And then you can assign the gain of each amplifier from sort of off up to 20 dB, or it's like 18 dB. But there's positive gain. It's not just an attenuator. And then you can assign the outputs. So you can assign either amplifier to either output, or you can assign them to be summed together on the chip. So it does mixing as well. So it does our volume control and our mixing and our bypassing and our input and output assignment all in one chip. And they cost 60-some cents and thousands.
Oh, that's great.
So, yeah, so I was able to find a chip that did everything I needed for 60 cents rather than going and getting the $7 chip. So that's why, and you got to think, a $7 chip means the pedal is $20 more expensive. And then it also needs a negative power rail, so you need a charge pump or something to get minus 5 volts or minus 9 volts, which adds extra expense. And then you need extra caps, and then you need extra filtering, and then you need to worry about this and that. So going with this chip means I can do everything on single supply. So what's going to happen eventually is we won't be able to make this version of the board anymore. We'll make a new version of the board that replaces this, probably with 2 other chips.
Okay.
When I do that, I'll get rid of this little analog switch. So this analog switch, again, my shame, it exists to do one thing, and it mutes the input to the DSP. So on the Marshmallow, it's actually not used. So every F13N, every syntax error, every wavelength, every Marshmallow, anything we make that doesn't have trails, Neomatic, Defender, it's not used. It's just sitting there costing me $1.
Oh.
So, but for anything that has trails, we use it. And the reason behind that is when you are doing bypass with trails, you want the delay to carry on or the reverb to continue to sound. So you leave the mixer connected. So whatever audio is going out continues to go out, but you mute the input to prevent new notes or new noises from entering the delay loop.
Oh, very cool. Okay.
Yeah, so all this does is just mute the input of that. Now, if I had it to do again, I would have found room for 2 of these chips on here instead of just the one, because 2 of these would still be cheaper than 1 of these and 1 of those. It's more board space, but I probably, I might have split this into 2 duals, like TLO 72s, and put them side by side here, and then I could use them as input selectors and volume controls for this, and I could use them for the muting, and it would be cheaper. The only bummer behind that is that the 3327 does not have any address pins, so you can't have 2 of them on the same I2C bus. I don't know how much I2C you've done, but
decent amount.
Yeah, so a lot of I2C parts will have like 1 or 2 address pins. Mm-hmm. So like an I2C part that we use all the time is we use the Holtec, the H16K33. It's a LED display driver chip. So Adafruit used it on all their little LED backpacks.
Yeah.
And we started, we bought like a couple, probably 1,000 of their backpacks over the years. And then we did our own when we switched over to alphanumeric displays. And so we use those. And they have 2 or 3 address lines. So you can have multiples on the same bus. So if you need a big display, So the whole tech has what, eight columns, 8 by 14 or 8 by 16. So you can have 8 digits for each one, or you could use it to control a big matrix of LEDs on everything. So, but if you've got 14, this is 7 segments. If you've got 14 segment displays, you do the math, but even 4 times 14 is, what is that? 56 LEDs total. So it becomes pretty cost effective to use a chip to handle that for you rather than trying to Charlie plex them with your micro or something.
Yeah.
But the whole tech has adders pins, but the on semi part does not. So if I wanted to use 2 of them, I would need another I2C bus, or I would need a bus translator. But if I give up some pins on this to do another I2C bus, then I have to give up pins for something else. So again, if I had to do it again, if I could go back in time to 2017 and redesign this board, I would go with the G part, more pins. I have 2 of these LVs on here. It would have saved me money in the long run. So, but I wasn't thinking about it at the time. When I designed this, I had a really clever MOSFET-based muting system that was going to be great and was going to work, and it sounded like utter garbage. So all the ones we took to NAMM that year had one of my favorite parts is a TLP222, which is an opto FET.
Okay.
So it's a little white dip 4, and sometimes they're black, but it's a little white dip 4, and it's got an LED on one side, and the other side is a pair of back-to-back MOSFETs. And when you have it off, it has a resistance of about a zillion ohms, and when you turn it on, it has a resistance of about 0.2 of an ohm.
Oh, wow.
So it just acts like a little SPST relay.
Very cool.
And it never makes any clicks or pops or any noise, and it's kind of garbage for running signals through in series, but for a shunt, where you're just trying to shunt something to ground, it's genius. It's so good. They're kind of expensive. They're about $1 in small quantities, but they're absolutely one of the best ways. It's one of the best ways of shorting a single thing to ground I've ever found. Way better than a mechanical relay. They use almost no current, a few milliamps. They can handle up to about 60 volts across the MOSFET, and a few milliamps, like maybe 1 milliamp or something, 5 milliamps, something like that. Like, they can handle a few milliwatts. They're pretty burly, but so every one we built had a TLP222 like hot glued to the top of the FD1 with some Bodge wires, and then when I laid out the board, there's a pin on here that's what is it, VDDIO, VDD core. So the VDD core pin I had tied to VDD, and so I put them on the board, and as soon as I put them on there, they would just pop. Like, I could program the chips. I couldn't do anything. I couldn't program the bootloaders. I couldn't do. You think? Can I program the boot? No, I couldn't even program the bootloaders. And I figured out that I had shorted that pin to VDD to 3.3 volts, and it should be just tied to a cap and sent to ground. So all the ones we took to NAMM had that pin lifted on the board in the air, bodged to a 0.1 microfarad capacitor.
Oh, I love it.
Soldered to ground, yeah. So there was a lot of. So I had 4 boards, and we made them work. And we had 4 working prototypes at NAMM, and so that was the syntax error, which is. Do I have one here? I should. It's one of my favorite pedals.
Yeah, that makes some really cool sounds.
Yeah. So this is my making noise board. This is the board I have at my house. There's not much on it. There is normally a Marshmallow right here. Mm-hmm. There's a Defender. There's a syntax error. There's a Super Neomatic, and there's a Radical Delay DX. So that's what I roll with. I mean, yeah, I have lots of other pedals. I have like 20 some pedals here. And at the shop, I probably have another 200 or so. But like when I get the urge to actually play something, it's probably going to be available to me on that board. So there's a website called folklore.org, and it's written by a guy named Andy Hertzfeld, who, was one of the early Apple developers, and later on he worked on the Mac team, and then he ran General Magic. But he's a really good programmer, and I read that website religiously, like every article on it, probably 10 times. And one of the things that always struck me is that he, and especially there's a guy named Burrell Smith, who was, again, one of the other he was the Mac hardware guy, had a real reverence for the way Steve Wozniak approached design. And I kind of see myself in that, not that I'm wise or ever will be, because I'm not. But the pragmatic approach that Steve Wozniak took when designing things, I strive to emulate that. So I don't do something in hardware if it's cheaper to do in software, and I don't bother trying to do complicated hardware stuff or software stuff if a chip will make it better. So
I like that.
A lot of the stuff that I do in this pedal is done in software because I can. But there's a lot of other stuff that's done in hardware because it's easier. It's actually cheaper and less hassle. I do whatever is the least hassle thing. So all the Neo pedals are pretty much the same. The difference is in the software. Syntax Error was first, and then we did all the other ones. And what's hilarious is that every time I do a new pedal, and it needs to do some new thing that wasn't available before, I have to write some new code for it. I almost always find that I put some kind of a hook or some variables in the original syntax error code like 3 years ago. Like the original syntax error code has tap tempo. There's a tap tempo module in the code. Like it doesn't have tap tempo. I never thought I was going to need tap tempo. But for some reason, I built a tap tempo module and I stuck it in there. I don't know why. It seemed like a good idea at the time. And then later on, when we did our first pedal that had tap, which I think was the quadrant. Yeah, quadrant. It was just there. It was waiting for me. I had to fix it because it was broken, but it was waiting for me.
Nice.
When I turned it on. Yeah. So, but there's a pretty vast array of different modules that exist now. So there's a sequencer module from the color theory. There's a pitch correction, pitch locking module. It's a scale table in the Marshmallow. So you can go and hold the center button and then hold the left button to change the scale. And when you use the pitch shifters, it will quantize to those values. So it's either chromatic or minor or major.
Yeah, that feature is really cool that it can just do that.
It's hard to dial in a specific pitch on a little pot when you've got a 2-octave range. It's very hard to get that pitch. Yeah, so all these guys are full of hardware and software tricks, and that's the fun part. One of the super fun things about these is that they're so limited. Like, you can only do a certain number of things with the FV1, and you can only do a certain number of things with the hardware as it sits. So if I want to do anything halfway interesting, I have to really, really stretch. So there's a lot of constraints, and working within those constraints sometimes can be really cool. Sometimes it sucks. It's like, oh, this won't do the thing that I wanted to do. Designing pedals that look like this, though, is probably going to turn off more people than it excites. It's a very polarizing pedal. Just the graphics and the art. A lot of people are.
I love it.
Excuse me. I love it too. And when I went to my designer, I said I want it to look like a box of breakfast cereal. I said, go to Aldi and buy a box of marshmallows and stars with the wizard on the front, and I want it to look like that. And he said, okay. So that's what it looks like. So that is definitely the inspiration behind this. It's very like Captain Underpants.
Yeah.
Breakfast cereal, Saturday morning cartoon. It's very much that. And then when you play the pedal, it sounds like that.
Yeah, it definitely does.
One of the things, and I've talked about this before, but one of the things that I do when I'm designing a pedal is I come up with a name first. I come up with the name of the pedal before I write any of the software, before I do any of the art. I have a name first, because it's really frustrating to come up with a cool pedal and then be like, well, what am I going to call it? Well, that's taken. Well, that's dumb. Well, that means barf in Spanish or whatever. There's like surprising number of curse words in foreign languages that are cool names. So I come up with a name first, and so I had the name Marshmallow, and it made sense. Like,
as I said, really fantastic conversation, super in depth, just going all in on this pedal, what makes it tick, and just super cool. I was in awe. It was such a great experience to chat with Matthew, and big thanks again to Matthew for taking the time to talk to me like that. Really appreciate it. Super nice guy. Check out Alexander Pedals. See what they're doing. As you can see, they're doing some cool stuff with music, tech, and guitar effects and everything. So, but that's going to do it for this video. If you liked it, toss me a thumbs up. Leave your questions or comments down below. I'll have applicable links down in the description. And until next time, this has been a very special episode of Blitz City DIY.